Hey everybody, Gabe Jenkins back with you. Still talking about materials. We are in the last session, we talked about what are the different types of materials. In the last two videos, we talked about some tests that scientists will do on materials to determine basically the strength of the materials measured in different ways, right? So we looked at the tensile strength test and the compression strength test, and talked about how those are similar kinds of tests. You're like basically applying a force on an object until it permanently deforms. In both those tests, you start off with a material and it was either being pulled apart in the tensile strength test or being squished together in the compression strength test. And then we're measuring how much force could they apply to a material, and at what point would it permanently deform? Because there's always a level of force that you can apply to something, and then as soon as you let go, it'll bounce back to its original shape. That's the elastic portion of a stress strain curve relationship. Elastic meaning it'll bounce back. But then if you apply more force than that, you apply more force in what's called the yield strength of the material. Right? A little bit more force than that, all of a sudden the material changes shape, it is deformed, it won't bounce back to its original length or its original shape, right? In both these cases, they were static forces, like the material itself wasn't moving. And so those are very commonly conducted tests to determine the strength of materials, specifically metals. We're talking about more than almost anything else here. We're gonna expand on that a little bit today and talk about a few more tests that determine how much force an object can absorb before it permanently deforms. And so we're going to talk about a couple of things first. We're going to talk about the bending test and the shear test. Okay? And then the second part of this presentation is going to talk about various tests to determine how hard materials are, meaning like how much force do you have to apply just to kind of like dig into them, basically. All right? So that's what we're talking about today. We're talking about the bending tests, shear tests, and hardness tests. All right, so let's look. I think the bending test is pretty sensible, to be honest. It's you taking a length of metal, usually, and you're applying an upward force on the two sides and a downward force in the middle. And you're basically measuring how much force do you have to apply in those directions to make it permanently deform. Obviously, if you imagine like holding like a little like a paper clip, you can kind of give it a little squeeze up and down, like do your own bending test, and it'll bounce back. If you press just a tiny bit, it'll bend for a second, and then it'll bounce back as soon as you stop pushing on it, right? But if you press with enough force, it's going to permanently change the shape of the paper clip. There's a couple of different ways that they do the Flexure test. Sometimes they just have two pressors down in the middle. It's called a 4-point bending test. Sometimes there's just one source of force in the middle. That's called a 3-point bending test. But the basic idea is still the same. What you're measuring is the force and how much force has to be applied to an object in order to make it permanently deform. Now, if you're just thinking about it logically, right, there are some very predictable factors that determine how much force you have to apply on an object to make it deform, right? One, how much force, both in the upward direction and and in a downward direction in the middle, right? But it also depends on the shape and length of the material itself, right? If you had a paper clip that's super long, right, that's might be easier to permanently deform. If you have a paper clip is a very skinny piece of material. The cross section of a paper clip is very small, right? If you were to cut it, tiny little surface area on the inside. If you were to take a giant beam, like a giant I-beam that they used to construct big skyscrapers out of, it's obviously going to take a lot more force to make that deform, right? So the calculation of the yield strength of a material given the flexure test or the bending test is going to depend on the force involved. It's also going to depend on the cross section of the material, right? The cross-sectional area of material. If it's a bigger cross-section, it's going to be a lot harder to make it bend. And it's going to depend on the length of the material, okay? Obviously, if all those forces are right next to each other, it's a lot harder to make it move. Now, if you just imagine this as one length of material, imagine it's like an I-beam on a building, right? If you push down on it, the top part, because it starts to bend a little bit, the top part, like the atoms that are right here, are going to be squished this way. The atoms that are right here are going to be squished this way. So on the top, there's a compression force. On the top of the material, there's a compression force. They're being pushed together. On the bottom, because the material in the middle is being kind of pulled this way and pulled this way, there are tensile stresses on those materials because they're being pulled apart. Right? I hope that makes sense. And eventually what happens is, on a bending test, the tensile stresses that are on the bottom become too great and the material pulls apart and is permanently deformed and fractured. Okay? That's ultimately what you're doing on a flexure or bending test. Some materials, if you're talking about ceramics, they have a little bit of flexibility but very little plasticity, meaning that they're not gonna bend much. They're just gonna kind of break, right? And so they don't flex a lot. They do a little tiny bit, but not a lot. And they basically just as there's they stay where they are until they fracture, right? There's not a lot of like bending and bouncing back with ceramics. Metals do tend to bend before they fail. And so this is what I was talking about a second ago. Failure occurs in any material because the tensile strength of the outer fibers are exceeded, right? It's like how much they can pull apart are exceeded, and eventually it's like a tensile test on the bottom and a compression test on the top. The bottom parts become pulled apart with too much force, and they give, and they just kind of they fracture. Okay, we're not going to get into the math. I'm not going to ask you to understand or calculate anything based on the math here. I wanted you to see that it exists. It's all pretty logical, actually. The transverse rupture strength, which is like how strong the material is a function on the positive side of the force. So the more force is required to bend it, stronger, and the length of the material. If you're talking about a very long piece of material, it's more force is required to make it break. And then the B and the T down here represent like the length and the width of the material, and it's squared. So it's just basically implying that you have to have a lot more force to permanently deform something that is that's a bigger cross section. Okay, where I'm not going to ask you to know. Basically, when it comes down to the flexures, I want you to understand like what is actually being tested, meaning like what does the test look like? Right? Pushing down in the middle, pushing up on the sides, you're bending it, and there's a point at which enough force, but depending upon the length and the cross-section of the material, there's enough force being exerted on it that it's going to permanently deform, and it's going to permanently deform because the stresses on the bottom part are being pulled apart too much, and the stresses on the top part are being compressed too much, and that's going to cause the material to break. All right, so that was the bending flexure test. The second type of test, which this is the last of our static stresses tests, right? So there was tensile strength test, compression strength test, the bending or flexure test, and then lastly here of the static stresses, static meaning you're not moving, is the shear test. So this is where you take a material and you apply differently direction forces. So in the sense, it's kind of like in a sense, it's like the bending test because you're applying forces in different directions. But in this case, you're applying the opposite directional forces to the same portion of the material, and you're essentially saying, okay, if I'm pushing the material left or to the right on one part and left on another part of the material, like same block of material, it's gonna like kind of deform a little bit. It's gonna stretch a little bit. It's gonna be a little bit elastic. It's gonna kind of stretch a little bit and bounce back. But what you're really seeing is how much force do you have to apply for that cross-sectional surface area to make it permanently deform in this way. If you're having trouble visualizing it, it's like imagine taking a cardboard box, right? If you kind of keep the cardboard box bottom stable, you're not letting it move at all, and you're kind of just like pressing, you're kind of like pushing the top of the box to one direction, it'll bounce back, right? It'll bounce back, but if you push it enough, all the little fibers in the corners are going to break, and it's not going to be able to bounce back to that same shape, right? So the shear test is measuring the force, and it's also thinking about the surface area that that force is acting over, right? So the surface area meaning like how big the top of that box is, okay? And you're measuring both how much force is applied, the area, and ultimately what you're measuring is how much the box is deflecting. How much is it moving to the side based on that force that you're applying to it? Okay. Again, I'm not going to ask you to do this math, like I wasn't going to ask you to do the bending flexure test math, but I just want you to see that it's defined in a similar way that the tensile strength test and the compression strength test is measured, right? The stress, again, it's like a force. The force is force per square per surface area, basically, right? So just like this was similar to the tensile strength test. It was force over surface area defined how much stress you're putting on an object, and strain similarly is measuring how much it's moving over compared to its original starting point. The graph is also similar to the tensile strength test in the sense that there is an elastic region where you can push it a little bit, you can apply a little bit of force over that surface area, and if you let go, it'll bounce back to its original shape. This straight line portion is the elastic region, just like in the tensile strength test. There's a certain amount of force that you can apply to it where it will bounce back. But you're gonna hit a point, whenever you do these shear strength tests, you're gonna hit a yield point where if you exert more force than that over that surface area, it's gonna permanently change shape, right? And that's why the graph starts to turn curved, and it means that you have to apply less and less and less force per surface area to get it to strain more and more and more, to turn more and more. You've probably even done this. If you played with cardboard boxes, you know that sometimes they're very strong in the beginning, but once you kind of reach a certain point, as soon as they kind of like give a little bit, it becomes very easy to push them over to the side. That's the plastic region, and eventually a material will break, right? Cardboard box isn't really going to break, but a piece of metal would break. It would fracture, okay? It would shear right down the middle. So that is the shear strength test. I'm not going to get into this. There's a shear modulus, so just like there was a modulus of elasticity, there's a shear modulus as well. That's kind of like a typical value for any given material that measures the relationship between stress and strain for a given material. For most materials, it ends up being a kind of a fraction of, it's like 0.4 times the elastic modulus. And so there's usually a predictable relationship between the shear strength of a material and the tensile strength of a material. But I'm not going to ask you to know this. I just want you to understand that there usually is a relationship between the strength of a material in terms of its shear strength and its tensile strength or compression strength. All right, so that was it for the various stress tests and the strength tests for material. Scientists also do a bunch of hardness tests, right? So hardness, again, this whole thing is talking about different properties of materials. Strength, hardness, and we're going to talk about how those change with temperature in the next presentation. But hardness is simply how resistant a material is to permanent indentation. That's what hardness means, okay? And if something is really hard, if it has good hardness, it generally means that it is more resistant to scratching and wear over time. So that's usually good for any kind of material where you want it to remain scratch-free, right? Side of a car, you want it to remain scratch-free if possible. More importantly, in a manufacturing context for us, is that like all of the materials that we're going to use to cut using the mill or the lathe, they have to be harder than the material that they're cutting, right? Because if you scratch one on the other, you need the cutting tool to be stronger, harder, I'll say. You need to be harder than the material you're cutting, or else it's not going to cut it. It's going to cut the cutting tool, right? And so in manufacturing, generally, if you're buying harder and harder cutting tools, they cost more because they're harder to manufacture, because it's harder to get hard materials into, it's more difficult, more expensive to get hard materials into a cutting tool shape because they're harder, right? Makes sense, I think. All right. Hardness tests are very commonly used for assessing material properties because they're usually pretty quick and convenient, as you're going to see in a second. Conducting the tests is pretty darn simple. And there's a variety of tests you can do. It depends on what kind of material you're working with, what kind of tests you'd want to do, and what kind of hardness you're trying to measure. But the two most common ones that I'm going to show you in a second are called the Brinell test and the Rockwell test. They're similar. They're very similar, and I'll show you two more tests that scientists do as well. So the first one we're going to look at, is the Vickers hardness test. I'm going to ask you on a quiz. I'm going to ask you like basically to identify, based on the photographic evidence of the test, what type of test was used in order to conduct this, and I'm going to need you to be able to explain how this test works. Okay.
The Vickers hardness test. The hardness of a compressor wheel for a turbocharger is to be measured using the Vickers method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece and then to evaluate the surface area of the indentation.
Pyramid shape, so the cross-section is going to be a diamond.
First, the tester has to prepare his testing machine. He takes the Vickers indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine.
Sorry, I should say the cross-section is more square. Maybe it's a rhomb.
He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With the control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length of the 2 diagonals. Finally, he only has to push the input key. The Vickers hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A in square millimeters.
Okay, so that's it. Vickers test. The little piece down here is a diamond. Why is it a diamond? Because diamonds are the hardest material we know, right? So it's a diamond that has been cut into the shape of a pyramid. So it's going to be a square, or, it's going to end up being I'm going to say a diamond shape, rhombus shape. Not sure geometrically what's exactly right, but it's a squarish on its side shape. And they press down with a known force, and then they measure the surface area that was indented into the material. And by taking the force divided by the surface area, they can measure how hard that material was that they just tested. Pretty simple. This next one, the Brinell test, is a very similar test. It's usually done for less hard metals, things like aluminums or lead or something else that's less hard. And in this sense, the test is conducted almost exactly the same way. They have a very hard sphere instead of a pyramid this time. It's a sphere that gets pressed into the material, and when they press it in with a known force, it's going to dent into the material, and the shape it's going to kind of dent in there is going to be a circular shape. And so they're going to be able to measure, and they know the diameter of this ball, and they're going to measure the diameter of the circle that gets indented into the specimen, and they are able to calculate based on the force and the change in the diameter, how big this diameter is here, how far it went in, and that's a measure of the Brinell hardness test. The math is more complicated. I'm not going to ask you to do the math, but again, the math is basically you're measuring the force divided by the amount of indentation that has happened as measured by the diameters of the ball, the original ball, and the indentation itself. Okay? Again, The math gets crazy. Not going to ask you to do that. The main thing on this slide is this. Force divided by the area of the indentation is what they're actually trying to get to when they do the Brinell hardness number.
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it. The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters.
Again, hardness is defined as force.
The result is displayed on the bottom left-hand corner of the screen and amounts to 250.
That's it for the Brinell hardness test. The Rockwell hardness test is slightly more complicated. What happens is they push in a kind of a sharp, a conical shaped indenter into the material. Then they push down farther, and then they let it back up. And they're measuring a few different distances in here. What they're really trying to measure is how much it bounces back once they've indented it. Okay?
The Rockwell hardness test, scale C. In this video, we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point.
Okay.
In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice.
So what they're really trying to do is they're trying to make a very minor indentation, then push it down, but they understand that as soon as they take that force up a little bit, the material is gonna bounce back a tiny bit, and they're trying to measure how much it has bounced back.
The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines.
Okay, so the first two tests, Vickers and Brinell tests, are measuring surface area as kind of the thing they're measuring. They're always measuring force, how much you're pushing down. But in the first two tests, they were measuring the surface area that was actually dented, right? Here, in the Rockwell test, what you're really ultimately measuring is you're measuring a height as opposed to a surface area that's being dented in by a certain force. Okay, so that's the Rockwell test. Last one is very different. So the first ones are like slow-moving things that are kind of pressing into a material and seeing how much it changes its shape. Sharpie impact test is very different. They take a big pendulum and they swing it down and smack a material. That's why it's an impact test. And you're swinging down with a certain known mass of an object, a certain height, and a certain known force of gravity. So if you've gone into any physics and you know about potential energy, this is gravitational potential energy that they're measuring. How much gravitational potential energy did it start with? Then it swings down and smacks the material, and then they're measuring how much it had at the bottom. Okay, so it's a totally different test.
The Sharpie impact test. The standardized Sharpie impact test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is M times G times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV.
So just to be clear, only gravitational potential energy at the top. It swings down. It hits the sample material, which absorbs a lot of that material, a lot of that energy, and then it keeps swinging, and then it has less gravitational potential energy at the bottom because it's less high. Small h is lower than big H, and if you know anything about gravitational potential energy, that means that it has lost some of its energy from the time it was up here. The pendulum has lost some of its energy from the time it was up here compared to when it was down here. All of that energy was transferred into this the specimen at the point of impact until it broke it. Okay, so it's measuring how much energy it took upon impact to break that material. So we're not talking necessarily about indentations, we're talking about breaking. But certain materials are going to have different characteristics, amount of energy it requires to break them.
It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed.
Whoa.
Such and the impact placed on the support and centered. Instead, it was pushed through the counter bearings under heavy plastic.
My bad, everybody.
Fracture surface has been.
So you can see right here, this was the part where it was kind of where the original notch was. All of this just meant that it was broken. It was brittle up along this edge here. So what you see here are just the grains of the metal, and the whole thing just snapped, right? So very little of it was actually deformed, and it was just pretty much snapped.
Formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behavior due to the strain aging effect.
Again, she used the word brittle. Brittle just means that it doesn't deform, it just breaks instead, fractures.
Second test. The second specimen has been made from normalized steel S235. It is also placed on the support and centered. The tester turns the drag indicator to its starting position, rechecks all safety measures, and releases the pendulum. This time, the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here, the specimen did not break into two pieces. Instead, it was pushed through the counter bearings under heavy plastic deformation. The sharp counter bearings under.
So you can see here, it bent, right? It didn't just snap, it exhibited more strength. It took more impact to snap it.
A heavy plastic deformation. In comparison with the strain-aged steel, the normalized steel absorbs much more notch impact energy and behaves in a very tough manner. The Charpy impact test is not only carried out at room temperature.
We're going to learn more about the effects of temperature, specifically raising temperature, and its effects on a material's hardness, and its tensile strength and compression strength and all that stuff in our next presentation. But you'll remember that we talked about crystals, like the grain crystals inside metals as having different shapes. Those have a direct impact on how materials act when they're put under pressure and under strain and under stresses, right? So like whether it fractures upon impact or whether it can stretch and absorb some of that energy.
Materials with body-centered cubic crystal structure, such as plain carbon steels, show a characteristic S-shaped curve of the impact energy versus temperature. In the so-called upper shelf region, the material absorbs a lot of energy and behaves in a tough manner.
So if you take a second and think about what this graph is showing you, right? At very low temperatures, which is, T is for temperature, very low temperatures, it's not able to absorb much of that impact energy at all. We're talking about body-centered cubic specific crystal shapes here. But as soon as you get to a higher temperature, it's able to absorb much greater energy upon impact than it was when it was cold. That kind of makes sense. If you think about cold things tend to break more easily. That is definitely true of body-centered cubic structure metals. But not all metals exhibit the same kind of tendency to change its behavior in different temperatures.
At low temperatures in the lower shelf region, only a small amount of impact energy is absorbed and brittle fractures occur. Metallic materials with a face-centered cubic crystal structure, on the other hand, do not experience a ductile to brittle transition. These materials retain their ductile behavior towards low temperatures and are therefore well suited for low temperature applications.
So that means that if you're trying to change the shape of some materials with face-centered cubic structures, you can work with them more easily at lower temperatures without having them just fracture right away. Some materials you have to heat up in order to get them to change their shape without fracturing, without just breaking, right? And some materials you don't. And again, that's just a characteristic property of specific grain structures and specific materials, therefore, that arrange themselves into grain structures that match things like face-centered or body-centered cubic shapes. Okay, just wanted you to know that exists. We're going to talk about the effects of temperature on different materials, on different strength properties. In our next presentation. Okay, so this is what we're going to next. But for now, that's the end of this video. Have a good day, everybody.